Welcome to another deep dive. Today, we're plunging into a really fundamental concept in computer science, something that crops up more often than you might think, the heap data structure.
It really does. It's one of those, you know, elegant building blocks. Once you kind of grasp how it works under the hood, it just unlocks some incredible efficiency for certain kinds of problems.
Absolutely. And we've got some great material to work with today. We're drawing from some pretty detailed research and notes, specifically looking at a section from a key algorithms guide that really lays out heaps and their operations quite clearly.
Yeah, and our goal here for you listening is to give you a really solid, kind of sticky understanding. We want to make it clear what a heap actually is, show you exactly how it's built, and importantly, how it stays organized.
And reveal why it's so efficient, right? And where its practical power lies. We want this clarity to, stay with you long after this.
Exactly. Let's get into it.
Okay, so let's unpack this, starting right at the beginning. What actually defines something as a heap? What are its core characteristics?
Okay. So at its heart, a heap is a specific kind of binary tree. And the material we look at really emphasizes two crucial properties it absolutely must satisfy. First off, it has to be a complete binary tree.
Right, complete binary tree. That sounds pretty specific. What does that actually look like? What does it mean in this context?
It means the tree is filled up level by level, right from the top.
Sure.
Every level, except maybe the very last one, has to be completely full.
Okay.
And that last level, if it's not full, it must be filled strictly from left to right. No gaps allowed until you hit the very end.
Ah, I see. So it's packed tightly towards the top and left.
Exactly. And the structure isn't just like an aesthetic choice. It's key because it makes using an array to store the heap super efficient. We'll definitely circle back to that.
Got it. Neatly filled, left aligned. So what's the second property then?
That's what's called the heap property. And this is all about the value stored in the nodes. It governs the relationship between a node's value and the values of its children.
And there are two main flavors, right? Based on this rule.
Correct. You've got min-heaps and max-heaps.
Okay, so in a min heap, I'm guessing min means smaller.
You got it.
Right.
Every node's value has to be less than or equal to the values of both of its children.
Yeah.
So as you kind of move down the tree from the root, the values generally tend to increase, or at least they don't decrease.
And for max heap, it's just the mirror image.
Precisely. Every node's value is greater than or equal to its children's values. So values generally decrease or stay the same as you move downwards.
Okay. And structurally, the node at the very top is the root, obviously. And the last node added, conceptually, is the one at the bottom rightmost position in that complete tree structure.
Yep, simple enough labels. But here's where that heap property min or max gives you this really powerful guarantee, because that parent-child value relationship holds true everywhere, all the way down.
The value sitting right there at the root, at index 0, basically, is always the most extreme value in the entire heap.
Exactly. For a max heap, the root holds the absolute largest element. For a min heap, it holds the absolute smallest. And having that extreme value instantly accessible is, well, incredibly useful.
Yeah, that guarantee, the extreme value always being right there, ready to grab that, immediately makes me think of one of probably the primary use case for heaps. Implementing priority queues.
Absolutely spot on. Heaps are basically the go-to structure for building priority queues.
Yeah.
A priority queue is that abstract idea like a regular queue where you add items.
But when you take items out, they don't come out first in, first out. They come out based on their priority level.
Exactly. And if you use a max heap where that largest value is always sitting conveniently at the root,
then taking an item out naturally gives you the highest priority element, assuming higher value means higher priority.
perfect match. When you dequeue or pop from the priority queue, the heap structure lets you efficiently grab that maximum element.
It feels like because heaps are just so perfectly suited for this, that the terms priority queue and heap almost get used interchangeably sometimes, like in code or library documentation.
Well, they really do.
Yeah.
I mean, technically, the priority queue is the abstract data type, the what, and the heap is the concrete data structure, the how. But in practice, because heaps are overwhelmingly the best how.
People just say priority queue when they mean I'm using a heap implementation.
Yeah, pretty much. It's a very, very tight relationship, all built on that efficient access to the max or min element.
Okay, so heaps are great for priority queues. Let's talk about interacting with them. What are the standard operations you'd perform, and crucially, how efficient are they? Because that's often the deciding factor.
Right. The common operations you'll see are things like adding a new element, which is usually called push, or maybe insert.
Okay.
Removing the top element, the one with the highest or lowest priority, depending, often called pop, or sometimes extract max or extract min.
Right, getting the most important thing out.
Then just looking at that top element without removing it, which is typically peak or top.
Just seeing what's next. Uh-huh.
And then helper functions like checking the number of elements, size, and checking if it's empty is empty. Pretty standard stuff.
And the big question, efficiency. How do these stack up in terms of big O notation?
This is where heaps really, really pay off. For peak, size, and is empty, it's incredibly fast. Constant time, O1.
Makes sense. You're just looking at the first element or like a counter variable, no real work involved.
Exactly. But push and pop, the ones that actually modify the heap, they sound like they'd be more complex, right? Because you have to maintain that heap property afterwards.
Yeah, you add something or remove the root, the whole thing might be out of whack, you've got to fix it.
You do. But here's the clever part. Because it's a complete binary tree, its height is always logarithmic relative to the number of elements, and it's a balanced-ish structure.
Okay, so the height is roughly log base 2 of n.
Right, and the operations to add or remove an element and then fix the structure, they essentially involve moving an element up or down a single path in the tree from a leaf to the root or root towards a leaf.
And the length of that path is limited by the height of the tree.
Precisely. Which means the work involved is proportional to that height.
So push and pop are O log n.
O log n, both of them. Which is incredibly efficient, especially when the number of elements gets large. Think about the alternatives. Adding to an unsorted list is fast, O1, but finding the max takes ON. Adding to a sorted list might take ON if you have to shift things, though finding the max is O1.
Yeah, O log n for both adding and getting the max min is a fantastic trade-off. It really scales well.
It's a huge advantage for dynamic priority scenarios. And thankfully, as you hinted, most modern programming languages give you built-in heap or priority queue implementations.
Yeah.
You usually don't have to build the array logic and the Zift operations yourself.
You just instantiate it, maybe tell it if you want min or max behavior, sometimes with like a comparator function, and you're good to go.
Exactly. Makes them very practical day-to-day.
Okay, super practical. But for that deep, sticky understanding we're aiming for, let's really dig into how they're actually implemented. You mentioned that complete binary tree structure is perfect for an array.
Right. That complete binary tree structure, filled level by level, left to right, it maps perfectly onto a simple array or list. It's incredibly compact.
So you don't need, like, explicit node objects with left child and right child pointers like you might see in other tree implementations?
Yep. Not necessary here. The nodes values are just stored sequentially in the array. The tree structure, the parent-child relationships, they're all implicit, derived from the element's position, its index in the array.
Okay, that sounds efficient. How does that mapping work? If I have an element at some index I in the array, how do I find its kids or its parent just using math?
It's actually quite elegant and simple. So given a node at index I,
Its left child is always found at.
index 2 I plus 1, always.
Okay, and the right child, predictably.
Index 2 I plus 2.
Simple enough. What about going the other way? Finding the parent.
The parent of the node at index I is found at index I1, 2. And critically, that's integer division.
Ah, integer division. So it always rounds down. If I is 5, its parent is 5 to 1, 2 equals 42 equals 2. If I is 6, its parent is 6 to 1, 2 equals 5, 2, which also rounds down to 2.
Exactly. Nodes 5 and 6 are children of node 2. It works perfectly.
And this holds true even for the root. The roots at index 0, its parent would be 0, 1, 2, which is negative something. That's out of bounds, correctly telling you it has no parent.
Right. And similarly, if you calculate 2i plus 1 or 2i plus 2, and the result is an index equal to or greater than the current size of the array, that tells you the corresponding child doesn't exist.
That's really neat. Just simple arithmetic on array indices lets you navigate the tree structure without any pointers. I can see why the array is the go-to representation now.
It's space efficient and the calculations are super fast.
Okay, this array mapping is definitely key. So now let's revisit those core operations, push and pop, but specifically think about how they work with this array representation to keep that heap property intact. Let's start easy. Peek. Accessing the top element.
Right. We already established the root of the tree holds the max, or min, value. And in the complete binary tree structure, the root is always the first node. So in the array representation, the root is always at index 0.
So peek is literally just returning array. That's why it's O1.
Trivial.
Cool. Exactly. Can't get much simpler.
Okay. Now, inserting a new element.
Yep.
Push. Where does the new element physically go in the array first?
When you add a new element using push, you initially just append it to the very end of the array.
So you increase the array size by 1 and stick the new value in that last slot.
Yeah. Conceptually, this corresponds perfectly to adding a new node in the first available spot in the bottom level of the complete binary tree, maintaining that left to right filling order.
Okay, sticking it on the end is easy, but
Why?
surely just putting some arbitrary value way down at the bottom, potentially deep in the tree, is going to break the heap property, right?
Oh, almost certainly, yeah. If it's a max heap and you just added a really big number, it's probably now larger than its parent. Or in a min heap, a small number might be smaller than its parent. Violation.
So you need to fix it. How does that work?
Precisely. After adding the element to the end, we need a repair process. This is often called heapify up, or maybe more intuitively, sift up. You start at the index of the element you just inserted, the very last element in the array.
And you look at its parent, using that I12 formula we talked about.
Got it. You compare the value of the newly added node with the value of its parent. Let's say we're in a max heap. If the child's value is larger than the parent's value, they're out of order according to the heap property.
So you swap them.
You swap their positions in the array. Now, the element you inserted is one level higher, but it might still be larger than its new parent.
Ah, so you repeat the process, compare with the new parent, swap if needed.
Exactly. You continue this process comparing the element with its parent and swapping if the heap property is violated, moving the element progressively up the tree towards the root. You stop when the element is finally in the correct place, for example, no longer larger than its parent in a max heap, or when you reach the root, index 0.
Sift up. That makes perfect sense. It's like bubbling the element up to its correct level.
Precisely. And because you're just following a single path from the initial position up towards the root.
The number of comparisons and swaps is limited by the height of the tree, which we know is logarithmic.
And that's exactly where the O log n time complexity for push comes from. Add to n amortized, then sift up.
Okay, that's elegant. Add to end, sift up. Now, what about pop? Removing the root element at index 0. We know the value we want is right there, but you mentioned earlier that removing from the start of an array is typically slow because you have to shift everything else down.
You nailed the problem. Just deleting array directly would be an ON operation in most array implementations because of that shifting. Plus, it would leave a hole and mess up the complete binary tree structure mapping. So we use a different, much smarter trick.
Okay, what's the trick for efficiently removing the root?
It's basically a two-step process, followed by a repair.
Wow.
Step 1, you take the element currently at the root, index 0, and you swap it with the element at the very end of the array, the last element in the heap.
Huh. Okay, so the element we actually want to get rid of, the original root, is now sitting harmlessly at the end of the array.
Exactly. Which leads to step 2. Now you just remove that last element from the array. Popping from the end of a dynamic array or list is usually very fast, often O1. So we've efficiently discarded the value we wanted to remove.
Brilliant. But now we have a new problem. The element that used to be the very last one, probably some random value, is now sitting at the root, at index 0.
Right. And unless the heap was tiny, that element is almost certainly violating the heap property. In a max heap, it's probably much smaller than its children.
So another repair job is needed, starting from the top this time.
Yes. This is step 3. A repair process often called heapify down or sift down. You start with this new element that's been plopped into the root position, index 0.
And I assume you compare it with its children now, using the 2i plus 1 and 2i plus 2 formulas.
Correct. You look at the current node, starting at index 0, and its children. Let's stick with the max heap example. You find which of its children has the larger value.
Okay, find the bigger kid.
Then you compare the current node's value with that largest child's value. If the current node is smaller than its largest child, the max heap property is violated.
So you swap the current node with that largest child.
Exactly. You swap them in the array.
Yeah.
Now, the element that started at the root has moved down one level, but it might still be smaller than its new children at this lower level.
Ah, so just like sift up, you repeat the process but going downwards.
Precisely. You continue comparing the element with its children, finding the larger child for a max heap, and swapping the element down with that larger child if the property is violated. You keep sifting the element downwards until it's finally in a position where it's larger than or equal to both of its children in a max heap, or until it becomes a leaf node, meaning it has no children to compare with.
Sift down. Also makes perfect sense. The element that was out of place at the top sort of sinks down into its correct spot.
Yep. And again, this process follows a single path from the root down towards a leaf.
Which means the number of steps is limited by the tree height, giving us O log n again.
That's right. Pop is also O log n. Swap root with last, remove last, then sift down O log n. The crucial part in sift down, remember, is always swapping with the correct child, the largest one in a max heap or the smallest one in a min heap, to ensure the overall heap property is maintained throughout the structure.
Wow, okay. That's really clear now. We've gone from the definition, the structure, the clever array storage, and now the detailed mechanics of push, add end, sift up, and pop, swap last, remove last, sift down. It all fits together quite nicely.
It's a really elegant interplay between the data structure's definition and its efficient implementation.
So tying it all together, why is mastering this level of detail about heaps useful? What are the big picture practical problems where this stuff really shines?
Well, we keep coming back to it, but the most direct and common application is implementing priority queues. That efficient O log n for adding an item, push, and retrieving the highest priority item, pop, is exactly what you need for so many scheduling systems, event managers, or anywhere you need to constantly process the most important thing next.
Like in operating system task scheduling or maybe network packet routing.
Could be. And it's worth noting, the sources mention you can actually build a heap from an existing unsorted list of n items even faster than inserting them one by one. It can be done in O(n) time using a clever bottom-up heapify approach, so initializing a priority queue can be very efficient too.
That's much better than the O(n) log n you'd get from inserting n items one at a time. Good to know. What else?
The material also points out, almost as a fundamental consequence, that heaps form the basis of the heap sort algorithm. It's a well-known comparison-based sorting algorithm.
Right, you can use a heap to sort things. We won't dive into the full sorting algorithm mechanics here. Maybe that's for another time. But it shows the heap isn't just for priority queues.
Exactly. It's a core sorting technique too. And then there's a third super practical application area, finding the largest K elements in a massive collection. This is often called the top K problem.
Ah, yes. This comes up all the time. Like, show me the top 10 most viewed articles, the 5 highest rated products, the 20 most relevant search results.
Precisely. You often have this huge data set, maybe millions or billions of items, but you only care about finding a small number, K, of the extreme values, the largest or smallest. You definitely don't want to sort the entire data set just to find those few.
That would be incredibly wasteful. How does a heap help here?
It's a classic technique. Let's say you want the largest K items. You can use a min heap, but keep it limited to size K.
A min heap. To find the largest items? That sounds backwards.
It does initially, but think about it. You iterate through your entire huge data set, item by item. For each item, you look at the smallest element currently in your sidelog min heap, which is instantly available at the root O1 peak.
Okay.
If the new item from the dataset is larger than the smallest item currently in your heap, it means this new item belongs in the top K, and the smallest item currently in the heap doesn't.
Ah, so you kick out the smallest one from the heap,
Which is a pop operation on the min heap O log K time.
and you insert the new, larger item.
Which is a push operation also O log K time. If the new item isn't larger than the smallest in the heap, you just ignore it and move on.
So the heap always maintains the K largest elements encountered so far. By the time you've processed the whole data set, the min heap contains exactly the overall top K largest elements.
Not clever.
And much faster than sorting everything.
Way faster, especially if K is much smaller than N. The total time is roughly O(n) log K compared to O(n) log N for a full sort. It's a highly efficient and standard solution for this very common top K problem.
Okay, wow. So just to recap this deep dive then, we started with the definition. A heap is that special, complete binary tree structure combined with the heap property, either min-heap or max-heap.
Right, which guarantees that the root node always holds the minimum or maximum value in the entire structure.
We saw how that complete binary tree structure makes it perfect for storing efficiently in an array using those neat index formulas 2i plus 1, 2i plus 2, i1, 2 to navigate without pointers.
And then we unpack the core operations. Peak is O1 because the root is always at index 0. Yeah. Push adds to the end and uses sift up to restore the property in O log n.
And pop cleverly swaps the root with the last element, removes the last, and then uses sift down, comparing with children and swapping downwards, also in O log n, to fix the structure.
And we connected all that, how it works detail, to the why it matters, seeing heaps as the standard implementation for priority queues, the basis for heap sort, and a fantastic tool for solving the top key problem efficiently.
You really have gained, hopefully, a much deeper, more intuitive feel for this cornerstone data structure. It's such a great example of how choosing the right way to structure your data can lead to surprisingly efficient algorithms, especially for problems involving priority or finding extremes.
Absolutely. Understanding heaps gives you a powerful tool in your mental toolkit for tackling certain types of computational problems effectively.
Definitely. And maybe here's a final thought to take away from this. We've focused on how heaps efficiently maintain the most important element, the max, or min, right there at the top, constantly updated in all log n time.
Consider that fundamental idea, a dynamic structure that always keeps the extreme value readily accessible. Where else might that principle apply? Maybe even metaphorically.
Yeah, think about systems beyond code. Could it be managing project tasks where you always need the highest priority one next? Or processing information streams where you only care about the most significant events? Or even optimizing personal workflows?
What other kinds of problems, maybe ones you encounter day to day, could potentially be simplified or solved more effectively if you could structure them in a way that keeps the most important thing constantly and efficiently available right at the top?
Something interesting to ponder. Thanks for joining us on this deep dive.